this video, we are going to explore about two antenna parameters, radiation power density and radiation intensity. The first parameter we are going to consider is radiation power density. So from the name itself, it uh, means that it is something associated with the area. So if we use the term density, we know that it is something associated with the concentration in some particular area. So from the name itself, it shows that it is a power concentrated in a particular area. So the radiation power density of an antenna is the measure of electromagnetic power flowing through a particular area at a specific point in space far from the antenna. So this is defined as power per area. We are considering the spherical coordinate system. So the area is 4 pi r square. R is the distance from the center of the sphere to the particular area we are considering. So P is the power transmitted from the antenna, G is the gain of the antenna, and R is the distance. So S is the radiation power density. So from this equation itself, we can see that the unit of power density is watt per meter square. So in case of a isotropic antenna, we know that it radiates equally in all the direction. That means the gain is 1. So in that case, the power density will be P by 4 pi r square. So to know how this power density varies with respect to the distance, I'm going to consider a directive antenna. So this is just for a representative purpose to see how the power distribution is varying. So I'm going to consider a directive antenna, and let's assume that this is the power radiated from the antenna, and we are considering these areas. So first I'm going to consider this area which is at a distance r from my antenna. So in that case, you can see that this is the area covered by the power from the antenna, and the power density is P into G by 4 pi r square. If I consider more distance like this one, you can see that area covered at this distance is more, and you can see that the power density is getting reduced. You can see that the power in this area is getting reduced as the distance is getting increased. So the power density gives us the information about how spread out the power is spatially with respect to antenna. So this gives an information about what will be the power at some particular distance from antenna, and this information will give us an idea about the coverage of the antenna, because we can see that at this point the power density will be less and the coverage is getting reduced as the distance is getting increased. So this radiation power density gives an indication about the coverage. The next parameter we are going to consider is radiation intensity. So the radiation intensity is defined as power radiated from the antenna per unit solid angle. So this is the expression for it, and the radiation intensity can be obtained by multiplying the radiation power intensity by the square of the distance. So here is the expression: P is the power, G is the gain of the antenna, and uh, 4 pi is the total solid angle of the sphere. So the difference between the radiation power density and the radiation intensity is that in the radiation power density, we are considering the spatial distribution. So there is a factor r square here in radiation power density. But in case of radiation intensity, we are considering the angular distribution. So this is the solid angle. So if we have an antenna located at the center of a sphere, what we are considering is how the power is distributed in each solid angle. So instead of the spatial distribution, we are considering the angular distribution. As this parameter does not have any distance dependence, it is very useful in characterizing the directional properties of an antenna, because we can see that it is only depending upon the angular distribution, no distance distribution. So this radiation intensity can be used to identify the directivity of the antenna. That is the difference between radiation power density and radiation intensity. In radiation power density, it gives an indication about the spatial distribution. In radiation intensity, it gives an indication about the angular distribution. To give a better understanding, I have considered an analogy considering the light from the flashlight. Here you can see that this is the spreading of the light from the flashlight, and here you can see that as the distance increases, the area considered will be getting increased and the power is getting reduced. So the radiation power density gives an indication about the power distribution in a spatial coordinate. So how the power will be spread out, and it gives an idea about the coverage. But in the case of radiation intensity, instead of considering the spatial distribution, we are considering the angular distribution. So we are considering how the power is distributed in different angles with respect to the flashlight. So this gives an indication about the distribution of the power in an angular direction, or we can say that it gives an indication about the directivity of the antenna. So this analogy gives a better understanding about the radiation power density and radiation intensity. So I hope you get some basic idea about what is radiation power density and radiation intensity. And if you want to know more about the mathematical expression and how the power density variation can be seen in CST, you can watch further. This is just to show how the power density is related to the electric and magnetic field. So it can be explained on the basis of Poynting theorem. So we know that in electromagnetic waves, it consists of electric field, magnetic field, which are perpendicular to each other, and the direction of propagation is perpendicular to both electric and magnetic field. So the energy carried by this wave per time per unit area can be given by Poynting vector. So the Poynting vector is defined as the cross product of instantaneous value of the electric field and instantaneous value of the magnetic field. So we have to consider at a particular time what is that value of electric field and magnetic field, and that cross product gives an indication about the power density. So as the power density is the cross product of electric and magnetic field, its direction is perpendicular to both electric and magnetic field direction. So that is, it is in the same direction as that of the direction of propagation. So if we correlate the instantaneous electric field to the complex electric field, this is the expression. So instantaneous electric field is related to the complex electric field by this expression, where E is the peak electric field and it is the peak magnetic field. So if we want to calculate the total average power, it can be given by the expression half of real part of E cross H. So it is the same expression as this, but it is the averaged over the time. And here you can see that the difference is we have added the value half, and here we are considering the peak electric and magnetic field. So if we want to get an average power, we have added half because we have to convert the peak power to RMS power. Because if you want to convert peak power to the RMS power, it is like E by square root of 2 and H by square root of 2. It will become half. That is, the total average power density is given by half real part of E cross H. That means that the power density is related to the peak electric and peak magnetic field by the expression half of real part of E cross H. So we can see how we can get the power density from the electric and magnetic field using CST. Let's see that. So for the explanation purpose, I have taken a horn antenna, and here I have in far field result I have taken the electric field linear scaling, and here you can see the peak value of the electric field as 25.7. So I'm going to 25.7, and the peak value of the magnetic field is 0.0682. So we have seen that power density is multiplication of both E and H field and divide by 2. So I'm multiplying both electric field and magnetic field values and then divide by 2. So this is the power density. So it has to be 0.87. So let's see how it is. So you can see that it is 0.87. So it is defined at the reference distance of 1 meter. So we have seen in our explanation that for the power density will be getting decreased with respect to the distance because it is related uh, to 1 by r square. So if I want to see the power density at 2 meter, I can change this into 2 meter. So what will happen? So we know that it is related to 1 by r square. So if I change to 2, it will be uh, reduced by, because 2 square is 4, it will be reduced by 4 by a factor of 1 by 4. So this has to be the value for the power density. So here we can see that the power density has to be reduced by 0.21. So let's see. Here you can see that power density is reduced by the factor of 0.21 when we increase the distance. So power density gives an indication about the power distribution with respect to the spatial distance. That means with respect to the spatial distance, how the power is getting decreased. That value is given by this radiation power density. So here you can see that it is related to 1 by r square. So when the distance gets increased, the power density gets decreased. That's what we have seen in CST. So I hope you get the idea about radiation power density here. Thank you. If you find any of the videos useful, kindly support.